Okay, hello everyone. We are going to start chapter 6. By the way, I have a bad cold these days, so my voice is a little bit like lower than usual. Please understand. Let me know if it does not, if you cannot hear it well, then maybe I can do something else. Okay, let's start. Chapter 6 is about normal distribution. So like since the last chapter, we are studying parametric distribution families. So the idea is we are going to set a certain assumptions, and then under that assumptions, a small number of parameters can fully explain all the distribution. So to describe n plus 1 possible outcomes in a binomial distribution, we only needed two parameters. Two parameters can explain n plus 1 outcomes probabilities. Now, in this chapter, we are going to study the normal distribution. And as you can see from the name, it is the most important distribution in not just in statistics, but in any science, right? So, normal distribution deserves its name. It is normal. Everything else is abnormal. Uh, so the reason why I said it is important in this course, at least in this course, is that from here, every single random variable will be approximated to our normal distribution. So since chapter 7 and so on, we are going to solve everything using a normal distribution approximation. So that illustrates the importance. Actually, binomial distribution can be approximated to a normal distribution under a certain condition. So we are going to learn that later. Okay, so let's talk about this. And let's learn what is a normal distribution. There are relevant chapters in like any statistics textbook should have a normal distribution somewhere. So you should be able to find them easily. So let me start with another brain teaser. So I'm listing 5 random variables, and one of them is different from the other 4. A, amount of toll size coffee. B, the time when a bus arrives at a bus stop. And C, weight of a wild-caught salmon. D, speed of a car on highway. E, number of traffic accidents on a day. So you randomly choose a coffee or a bus or a salmon or a car or a day, then you can see the distribution. You should be able to see like realization, and then by repeating that, you can think about the distribution of these random variables, and one of them can be thought of as a different type of variables. What is that? The answer is E. I think the intended answer is the number of traffic accidents on a day, because the number of traffic accidents is countable. It is a count 0, 1, 2, 3, da da da. So it is natural numbers or integers, but all the other variables are continuous. That means it doesn't need to be an integer. Like for example, amount of a tall size coffee. I don't know exactly how much is it, 12 ounce? So but it can be 12.1 ounce or 11.99 ounce. So it doesn't need to be an integer. Similarly, time can be different by a second or 0.1 second. It doesn't need to be an integer. And weight, similar, like how big is a salmon? I don't know. Like say 10 pounds or 10.0001 pound is also possible. Speed is similar, like 60 miles per hour or 60.00001 or 60.1057 miles per hour is also possible. So in these 4 random variables, there is no increment. It is continuous, right? any number is possible on on certain interval. So if we think about an interval which contain all the possible values, anywhere is a possible outcome, right? That causes a big difference. So continuous random variable and discrete random variable are very different. And the simplest way to distinguish them is like this. If you think of a continuous random variable, there should be always another outcome in between 2 points, right? So for example, let's come back here. Like think about bus arrival time. So here a bus arrives at this time and another bus arrives at another time. And then you can always imagine another bus that arrives in between them. No matter how close they are, still there is a small moment. There should be at least a moment in between them, as long as two buses arrive at different times, right? Similar, coffee, amount of a coffee, like one coffee has this much amount, another coffee this much amount, and then you can think about in the middle between them, right? All these four random variables allow any possible, at least some possible numbers in between two realizations, but traffic accidents, like between 0 and 1, there is nothing. You cannot think of 0.5, like half accident at all. Like that is not possible. So between two outcomes, a continuous random variable has another outcome, typically infinite number of outcomes, right? Because if you choose, if you think about two outcomes and think about another outcome, and then you can think about another outcome in between those each pair of the outcomes. So in that way, you can choose another outcome in between them infinite times. So there should be infinite number of outcomes. But discrete random variables do not allow that. So as I said, like when you count, like count is typical, there is nothing in between 0 and 1, 1 and 2, 2 and 3. So you may not be able to find any possible outcome in between two distinct outcomes. That is a big difference between continuous random variable and a discrete random variable. Then you may think why that's important. It is important because it affects our analysis. So think about bus arrival time again. We are going to think about bus arrival time as a random variable. So then basically we need to study its probability distribution. We want to describe its probability distribution. And so far in the first, say, 5 chapters, what we did is we list all possible outcomes, right? So in binomial distribution, we thought about n plus 1 possible outcomes and calculated probability for each outcome, right? In the first chapter, we made 2x2 matrix and put in the probabilities in each cell. That is how we studied the probability distribution. I said if you have the full probability distribution table, you know everything. That was our approach. That is right, but that is possible only when we can list all possible outcomes. Now, we cannot write down all the possible outcomes for a bus arrival time, right? So there are infinite possibility. Like for example, suppose that what I'm talking about is you have to imagine that a bus arrival time is measured with super accuracy, like the Olympics timer, right? Like a nanosecond is measured, like the time when the bus crosses a certain imaginary plane here in front of you, and when the plane is broken, is measured by a super accurate timer. Then how much possibility are there, like up to nanoseconds, for example? you cannot list all possible outcomes at all. It is time is continuous, so one moment becomes one outcome, and there are uncountably many moments in any certain time interval. So our approach does not work anymore for continuous random variable. So continuous random variable requires a totally different approach to our to describe the probability distribution. So that is what we are going to study here. Our idea is like now, what we are going to do here is it is related to measuring the time interval, right? So instead of listing all possible outcomes, we are going to measure the length of a time or a time window, right? So suppose that the bus is supposed to arrive at noon, but it may arrive early or late, like say, and up to 10 minutes. So the possible time interval is plus minus 10 minutes. So total 20 minutes include 100%. So we are sure that the bus arrives in between minus 10 minutes plus 10 minutes. Okay, so 20-minute window contains 100%. And then one possible way to describe the probability is like this. I'm going to assume that if you define probability this way, let's say assume that the probability is proportional to the length of the time interval, right? So previously we know that 20-minute window contains 100%. Then under our assumption, we can think about like 10-minute window, which is half of the total window. Then because the length is half, the probability on 10-minute window must be also 50% proportionally, right? This is another approach to describe probability, right? You don't need to list every single outcome, but you just measure length. This will be the basis of our approach. You don't need to measure how many outcomes within interval. There should be infinite number of outcomes in any interval, so it doesn't matter how many outcomes there are, but what matters is the length. Then you can calculate probability for any interval. Think about this. Super easy question. So I gave you a time interval between 11:58 and 12:02. Then it is a 4-minute interval. So 4-minute interval is 1/5 of the whole interval, right? So probability should be also 1/5. That is 20%. Okay? Or you may think it this way. I assigned 100% on 20 minutes. That means each minute, 1 minute, has 5%. So 4 minutes should have 20%. Like same thing, basically the same approach. But you get the idea. We can now forget about single outcome. Single outcome does not matter at all, and there are too many of them. So we are going to measure the interval, all right? Then now you can think about this. What is the probability that the bus arrives exactly at noon? I said it is not a nanosecond earlier or later. It should be exactly at noon. What is that probability? So it can be tricky. The answer is 0%. 0. So it is impossible for a bus to arrive exactly at noon because it is a moment It is not a time interval. It is one moment on a time flow. On the time flow, um, one point has zero length. Mathematically, it is zero, right? You understand that, right? So the starting point and end point are the same. That is the definition of a moment, a point in a time. So its probability should be zero according to our approach. So you cannot exactly hit one point, right? This is true. This is not just mathematically true, but actually true because it is impossible to avoid a nanosecond, microsecond error. That is impossible. You can imagine that. So even it should be uh, exactly on time. And this is true for any continuous random variable. So one single outcome has one point has zero probability. Um, like for example, a tall size coffee cannot contain exactly 12 ounces, and you cannot drive a car exactly at 60 miles per hour. The weight of a salmon cannot be exactly 1 pound. So you cannot think about just one outcome. One outcome means nothing. It is not just about possibility. Like, oh, it is not possible to think about all the outcomes, but also, even if you can do that, it doesn't mean anything. A single outcome has zero probability. So, because of these two reasons, we cannot use the previous approach, listing all the possible outcomes. Even if you can list all the possible outcomes, the probability will be all zero. So, means nothing. And again, we are going to change our approach in this way. The new approach to define probability is like this. We are going to think about not just probability exactly 12 ounces. We are not going to use exact thing, but we are going to use probability that a tall size coffee has less than 12 ounces. Less than 12 is not just one single outcome, but a bunch of outcomes with certain interval, and probability that you drive a car faster than 60 miles per hour. So 60 or higher is another interval, or probability that a wild-caught salmon is between 1 and 2 pounds. So this is also an interval. So we are going to totally change our approach from considering one point to considering intervals. That is key difference between continuous random variable and discrete random variable. So in our statistical notation, we can say that if x is a continuous random variable, probability that a random variable x equals to a value x is always zero. Equality means nothing. Equality is nothing, so we have to replace equalities with inequalities like this. So we are going to think about smaller than something or greater than something. But also, in writing our inequality, smaller than or equal to, larger than or equal to, can be simplified to just smaller than. So equal to something has no probability, so we can ignore that, right? So I may switch between them when I calculate probability for a continuous random variable. So continuous random variable, again, does not have a probability on a point. Point has no probability. So inequality is used, and strong and weak inequalities have the same probability because including a point or not does not change its probability. Okay, that is our approach, and it goes back to the cumulative distribution function we defined in chapter 3. So we are going to use the cumulative distribution function, which is defined satisfy an inequality. So if you know this function, this is what we want. This is how we describe a random variable. So mathematically, this is the way you define a random variable. You characterize a random variable. So if two CDFs if two random variables have the same CDF, we say two random variables are the same. Okay. And later I'm going to show you that if you know the CDF, you can calculate any probability or like expectation, variance. Everything follows from the CDF. Okay. So the importance of CDF is based on this idea. We need to describe utility using inequality. Okay, so I'll continue in the next video. It gets too long, so see you in the next one.